Hello and welcome to Andy's workshop. This is going to be a follow-up video to my previous one where you saw me fiddling around with one of these that I bought on eBay. Now what it is a voltage regulator module, basically a power supply from a rack server. This particular one came from a Dell, I think it's a 2850 or so. And I thought, I'd have a play around with it, try and find out what the pinout is, because the idea behind it is, well, these are just so cheap to begin with. This on eBay, they're about, I've seen them go as low as £3. I bought this one for about £5 or £6, and it's certainly worth loads more than that. Because these things are going to be highly reliable units, very stable indeed. They have to be to sit inside a rack server and supply power to one of Intel's Xeon chips. So we had a play around, and ultimately we did find out what it is. It's made by a company called Artisan, and it's the actual serial number of this unit is an NXA66, and we were able to find the data sheet. So let me just grab it and I'll show you it here. There are two data sheets. One's like an overview and one's more detailed. This is the overview data sheet. It tells you a few things about it, and there's some nice things to know. In particular, it has two output voltages. It takes 12 volt DC in, and you can select either 3.3 or 2.5 on the output. Now it's a bit odd that it says 2.5 there, because in my experience, having tested this one that I got, the alternate voltage is actually 5 volts, which I think is a bit more useful. I mean, 2.5 is useful as well, but 5 volts is particularly useful. Now if we look at the nominal output current, a rating of 20 amps, now that's far beyond any of the kind of basic power supplies that you would buy on eBay or just from a local hobby store. So I thought it's definitely worth trying to get something, get this thing working. And it says the actual minimum, it's a switching power supply of course, the minimum efficiency is 86, 8 or 82%, so that's probably based on 3.3 or 2.5 as being the selected output. So given this information, and look, there's even the output current versus ambient temperature as well. It's a nice chart. Obviously the key information is the pinout here in this list. It tells you everything. So given that, I was able to design a power supply board for this. Now the idea is that I would plug my little module here into my power supply board, which is little more than a controller with some nice interesting features. And I should be able to make a power supply out of it, because I certainly don't have an existing power supply that can supply that level of 20 amps. That's really nice. So in this video I'm going to show you the board that I've made, and we'll play around with it a bit. I'll show you some of the features that I've built in, and we'll run some load tests as well using my electronic load. So let's get on with it. Before I show you the actual board that I've built, I'm just going to show you an important difference between these units. Now, the original one that I got is this. It's got a black heatsink. It doesn't say NXA66 on it. It has some Dell part numbers on it instead, and it says Rev A00. Now, this particular one has 3.3 volts as its primary output, and the alternate selectable output is 5 volts. I don't know any official way of identifying the 5 volt unit other than look for Rev A00, and the black heatsink's a bit of a giveaway as well. So I went onto eBay and I grabbed another one because this one was going for about £3 and I thought, why not? And this one has a silver heatsink and it says Rev A01 on it. This one has 3.3 volts, that's its primary output of course, but the selectable one is 2.5 volts. So that actually tallies with the data sheet that you can download. So if you're going to build one of these power supplies yourself, do bear in mind that if you get the one with a silver heatsink and it says Rev A01 on it, it's very likely to be 2.5 volts as a secondary output. Whereas if you're looking for the 5 volt one, try and get hold of the black heatsink version with Rev A00 on it. This one here. And this is the one that I use most of the time because I find 5 volts very useful. Right, let's get onto the board. So this is the board that I designed. It's a standard 10 by 10 centimetre layout board that you can get made yourself at one of the Chinese PCB prototyping houses, just like I did. I got it done in a green solder mask, so it would match the solder mask of the NXA66 that's going to plug into it, so it should all look nice and coordinated. The design is basically all through hole. I tell a lie. There's one part that is not through hole because it just simply isn't available in anything but surface mount. But it's easy one to solder, and I wanted this project to be as accessible to anybody at all who might want to build it. And I know some people do struggle with surface mount parts. So what I'll do now is I will walk you through the basic features of this board, how things are laid out, and then we'll quickly switch to the built version and I'll have a play around with it and we'll see what the actual the features do. Okay, so a quick look around the footprints on the board before we move on to looking at the built version and seeing it tested. So at the top here we've got 12 volts in. The NXA66 needs 12 volts as its primary supply. So the input header here goes through, the footprint here you can see is for a relay. I wanted a relay in between the power supply coming in and the NXA66, which obviously goes on this 50 pin header here. I wanted a relay in there because I don't want the thing to just power up as soon as power is applied at the back. I want a microcontroller, which you see here, see the footprint for here. I want this to power up first. I want it to be able to set all of the pins to the correct values, and only then can the microcontroller activate the relay and switch on the power supply. There's also another good reason for it as well. The VSP pin, which is the voltage select pin, the one that selects between 3.3 and the alternative supply, does not like being toggled while power is applied. If you do that, it goes all kind of crazy and stops regulating power completely and goes all over the place, so you basically just don't do it. So if the user being me, goes to the front panel and flips the VSP switch, which you could easily do while it's on, then I want the microcontroller to respond to that by turning off the relay, setting the new level on the pin here, and then turning the relay back on again. So you're effectively allowing VSP to be switched, even though the NXA66 doesn't actually allow you to do it while it's powered up. So yes, I mentioned there's a microcontroller here. That's the good old Atmega 328P that if you've, you hardly have avoided knowing about the Arduino. It's the chip that's used on that. Really simple to program, probably overkill in terms of memory. 32K is rather a lot for this project, but largely I think because of the popularity of the Arduino, the Atmega 328 is just so cheap. It's in quantities of about 5 on AliExpress. I think it works out at about $1 something. They're probably fake, but what the hell, they work. Okay, so you've seen the where the microcontroller is going to go, central to the board, and underneath here, bypassing the relay, is the 12 volt supply going to what here is a buck regulator. It's a switching buck regulator that takes the 12 volts down to 5 to be able to supply the Atmega 328 here. A switching buck regulator was chosen because stepping down 12 to 5 is rather a long way. And if I were to use a cheaper, standards LDO regulator, something like that, it would have to burn off that difference, that 7 volt difference as heat. And I'd rather not do that because it's rather a lot. It's wasteful for a start, and it could end up generating more heat than a package could handle. And I have to end up putting a TO220 package there with a heatsink on it or something like that. It's just not ideal. A switching regulator is far more efficient, so that's what we've got here. The footprints you see here are for a pair of 4-digit common cathode LED displays. The idea is that we'll be displaying voltage up here, current down here, constantly on bright LED displays. I chose LED because, for a bench power supply like that, it's my opinion that you've really got to have LED or VFD. VFDs are expensive to get in generic modules. I think it's Noritake or one of the Japanese companies does them, but they're very expensive. They're lovely, but yeah, too much. You need something with a big contrast, and those LEDs, the 4-digit LEDs that you can get on eBay for just a few pounds, really cost effective, and you can see them all the way across the room. And if they change, something you can see at the corner of your eye. If a digit changes, you just see it because it's so high contrast. Whereas if it was a TFT, there's a chance you might miss it due to poor viewing angles, something like that. So LED it is. And the controller for it is Max 7221. In the DIP format. Now this chip basically multiplexes the 7 segment, 8-digit 7 segments. So that's 56 possible LEDs. It multiplexes them all for you. So, and you talk to it from the MCU by an SPI interface. It's really simple. You basically tell it what to display, and it sets it and holds it. You don't have to do anything else. It'll just keep it there until you send it more commands. Loads of code to explain how to do this on the internet. It's a really simple to use device, so that's in there. We've got some status indicators down here. We've got power, we've got EN, which is output enable. We've got OK, which is power good. That's linked to the power good pin over here, which is driven high, I think. I remember which way around it is. No, it's not, because it's an open drain. It can't be driven high. It's driven low and pulled high, depending on whether the power is good or not. And we show that here on the LED. And we have the VSP LED, which just shows whether you've selected the alternate output or not. So back over here again at the NXA66, big 25 by 2 footprint here. It's basically an edge connector footprint, and we just plug the thing in. The output is here, this big plane, which is connected to all these pins. Some heat sinks to link it to a mirror of this plane on the bottom as well. So I meant fill, not plane. And here is the current sense, the footprint for the current sense resistor. It's I think it's a 2012 or something like that form factor. Very, very large form factor, because it needs to be, because it's meant to be able to take quite a lot of current going through it without getting too hot. The rating for that resistor is 2 milliohms, and I bought a 1% resistor for that. It doesn't, the accuracy, you don't have to get it with hugely brilliant tolerance, because you can calibrate the value of the resistor inside the INA226, and so basically you can get your multimeter out. You can measure it if your multimeter's got the capability of sensing that's low of resistance, and you can calibrate the INA226 yourself. Of course, that's the footprint for the INA226 there. It's a little MSOP 10 footprint, very small, but it only got 10 pins, 0.5 millimeter pitch. It's the only challenging, shall we say, footprint on this board, and I recommend when you build it, you do that one first. It's not that difficult. You can do it with good magnification, strong lighting. It's not too bad. I did mine with my reflow oven, of course, but you don't have to. It is possible to do it with a soldering iron. It doesn't have to look pretty, it just has to work. And you can see just inside the footprint for the sense resistor, if this will get the focus right, you can just see the tapping off there of the both sides of the resistor into the INA226 there, where it does the measurement. And on the output here, there's an output capacitor. I noticed that was recommended inside it was in the test results for the NXA66 datasheet, and so I thought, yeah, okay, we'll do what they did for the test as well. Put a large capacitor there. If I'd had my head screwed on a bit more, I think, and make it a bit more belt and braces, I would have put a bleed resistor across this so that it drains when there's no load. When you've got a load connected to it, it just drains immediately. But if you've got no load, then that cap will remain charged, and you'll see a voltage drop slowly on the display over here. It's not ideal, but it's just one of those sort of gilding the lily approaches would have been to put a bleed resistor across it. So the output is there, the return is here. You don't have to, it's a bit of a convenience here having the return. It looks nice just from the front panel to go to here, and there's a big fill here that takes it right up to the ultimate ground here. You could bypass that. If you want to be completely efficient, you would go straight from the front panel back to the power in here. Just miss the board out completely. There's no point in going back through the board. It just looks nice, and so that's why I've put that header there. Okay, so that's a quick overview. Oh no, there's one more thing to mention. That's the header for the USB ASP programming device. If you get one of those cheap ones on eBay, you just plug the header in there. It's pin compatible with the plug-in header with a little solder mask. Sorry, silkscreen rectangle there to show where the fat part of the connector goes. You just put that on, and you can program the firmware straight away with the thing powered up. Basically, when I was developing the firmware for this, I just had the board powered up all the time, and I just had the header permanently connected, and I just reprogram in a cycle and just keep testing until it worked. Oh yeah, and up here we've got it's the UART output connector. So when we want to test the connectivity to the, to do the data logging, it's through this header here. And I'll just mention this one. These pins are exposed because the NXA66 exposes them. They have a pin for current sharing. It's for load sharing, basically. You can put multiple NXA66s together on the same board, I guess, and they can share load currents if you need to supply more than the 66 watts, 20 amps that it can provide. I don't use it, being a QB6, I don't know how to use it, I've never tried it. And it has remote differential sensing here, sense plus and sense minus, so you can actually sense the, you can feed back to it the voltage at the load itself. Basically, I guess you're Kelvin connecting the load back to the sense here. Never tried it, don't know what it's expecting here in terms of levels. It's actually quite interesting to see what it would do in the presence of sense input. Maybe it would actually vary its regulation to try and compensate for drop at the load. That would be interesting. I mean, it is a sophisticated little module, so I wouldn't be surprised to see it doing that. Okay, so that's the blank board. As I said, mostly through hole, and what we'll see in the next section is the board populated, and we'll see some tests, and I'll put some load through it. Okay. Hang on a minute, I forgot something. I'm sure you're all shouting at the screen there, saying, what's this hole doing in the middle of the PCB? Couldn't you afford the rest of the board or something? So I forgot to explain what goes there. Basically, what we have here is a temperature sensor connection. So it's a connector for the microchip MCP9700 thermistor. It's a linear compensated thermistor, which I'm going to use to be able to monitor the temperature of the heatsink here. And the idea of the hole is that you connect the temperature sensor here, you run the leads through the hole here, underneath the board where they look nice and neat and you can't see them, pop out the back, and I can attach the temperature sensor itself directly to the heatsink of the NXA66, roughly where the power MOSFET is, the bit where it's going to get hot. And in conjunction with that, there's another header here, which is for a fan. So the idea is that you'll be able to program thresholds for switching a fan on and off inside the MCU here. So when the temperature exceeds a certain value, you'll turn the fan on. When the temperature falls back down below a preset value, you'll turn the fan off. Simple as that. And just to help with that, because we're doing analog sensing here, the MCP9700 is a thermistor and it outputs a single analog voltage. We'll filter the analog voltage supply and the analog reference with a simple LC filter to try and keep it stable here. Right, so now I really have finished, and we'll get on to showing you the actual board as it's been built. So here it is, all built up and ready to go. It was really simple to put together, although it did take quite a while. I actually find it takes me longer to put together through-hole projects than it does to SMD ones these days, because of all the the bending, the turning the board over, soldering, trimming, and so on. But what you end up with at the end is a nice chunky-looking board with lots of bits and pieces on it, and I do like that, I have to say. So everything is where it should be. Of course, there's the relay, there's the NXA66 in its slot. The MCU, the two LED readouts. These are pin headers for the controls. These are the headers for the power in at the top and power out at the bottom. I've got the temperature sensor going out there. I made that out of basically I had a fan connector lead which I just trimmed. The leads go across the bottom, and then I fitted on the temperature sensor on the end, heat shrunk some protection onto the leads to make sure they don't short, and then crudely taped it onto the back of the heatsink, right at the point where the power MOSFET is there, the hot part. So I'll be able to sense the temperature nicely, and the leads fit nicely through that hole. And up there, of course, we've got the step down buck regulator. Before I switch it on, I'll just quickly note that for these pin headers, when you're buying them, you can get them on eBay for really cheaply. And this is what I used for the controls here, because it doesn't really matter about the quality; they're just switches. But for these, I used good quality items that I got from Farnell, that are from a real manufacturer. They're rated for greater than 20 amps of current. So for the ones that are going to handle power, it's best to use something that you have a some kind of quality manufacturer behind it. But for the switchgear settings, it just doesn't really matter. You can get those off eBay and save a few quid. And of course, there's the current sensing IC down there. I mentioned that earlier on. It's the INA226. Let's have a quick look at the data sheet for that, because I've got it right here. I've got the front page of it printed out. It's by Texas Instruments, and as it says there, it's a bidirectional current and power monitor with an I2C compatible interface. I found this really, really simple to use, and it's why I used it. If you look at the block diagram down here, it requires almost no external components apart from the obvious ones. If you see the block diagram here, you have the current sense resistor here. You need that, clearly. It's fundamental to the design, and it can't be internal to the chip because it's going to handle quite a bit of current, and you don't want that inside the IC. It just can't handle it. So in my implementation, I'm doing a high side shunt, so it looks exactly like this block diagram here with the resistor up at the top. I'm not doing the low side, I'm doing the high side shunt, so it comes out to the load. The tap off from the current sensing resistor goes into the INA226, where there's an ADC. The ADC converts to digital, and then the internal circuitry handles the I2C interface on the other side. And of course, all you actually need to implement I2C is a couple of pull-up resistors for the bus, and the IC itself requires a decoupling cap, and that's it. It's really a really simple device to use. And I was quite pleased that it actually worked first time when I put it all together. Really good. Oh, and it works in a wide range of sort of power supply environments as well, 2.7 to 5.5. So it'll work in the common 3.3 and 5 volts environments. So now we've seen that and the board's ready, let's plug it in. Now, the one thing to quickly note before, I know you won't see it working, but just quickly note, I don't have a case for this yet, and I do rely on these switch gears for testing. So I'm going to quickly hack together some strip board with some switch gear on it. It's going to be a hack, but it'll allow me to operate these things for the purposes of testing. So let's see how we go. Right, it's all hooked up for testing, and I'll just explain what we've got here. This is my hacked up switchgear board. Basically, it's a bit of strip board with a couple of switches carelessly soldered into it, and also the rotary encoder, which has a button on top of it. They are plugged into this little breadboard, and from there I use some jumper wires to just hook them into the front panel there. Hope they'll hang together for long enough for me to be able to actually do a demo and some testing. They're not exactly done in a kind of professional way. So the output here goes up. I'll just move the camera so you can see where it goes. It goes up to my DC electronic load. That's an iTech unit there. It's basically the same as a BK Precision, but a lot cheaper because it hasn't got their badge on it. I'm actually surprised. I use this a lot more than I thought I would. It's a really useful device. It can do constant current, constant voltage, constant watts, and constant resistance. It can also do programmed battery drain tests. It's actually really quite useful. This model is the IT8511 Plus, and I got it on AliExpress. Probably costs more now if you're English and you're buying it from there, because they're priced in dollars, and you know what's happened to the currency recently. But if you're from America, you can probably still get it for a decent price. Now, going back down to the board, the inputs at the back here, a couple of crocodile clips going to my bench power supply, which is set to 12 volts. That power supply has a limit of 3 amp output, so I won't be able to go any higher than that during testing. And the wires that connect them up are nice hefty things, 2.5mm core wires, which are generally used for mains connections. So hopefully I'm minimising losses on the cables. There will still be losses, but using a big fat cable like that does minimise them. And just for fun, I've hooked up a little 40mm Gelid fan there. That's the one that I'll be mounting on the case, so I can show you the temperature controls working. Okay, so I'll just lean over and switch it on, and we'll see what happens. And it's on. Starting up. Oh, and you can't see that. Can you read that? I can't read that. The problem is I'm shooting this under an 80-watt fluorescent lamp designed for photography studio purposes, and it's bright. It's just washing out the LED there. Let's see if I've got a filter lying around. I should have one. Oh, here's one. Yes, I was using it for a cup mat. Let's see if you can see through that. That's better, isn't it? You can actually see the readout. I think for the rest of that this demo, I will run this with the lights off, so you won't be able to see anything apart from the display, but that's probably all you do need to see. So let me just sort that out. Lights out. I don't know how the camera's going to cope with this, but yeah, right. So do a quick demo. I'll turn on the alternate voltage and we'll see what that measures. 5 volts. You heard the relay click in and out there, I hope. So that was basically switching the power, the NXA66 completely off, changing the voltage select pin and then putting the relay back on. Now let's turn the output enable off because it's currently on and see what happens. Now what you're seeing there is now the current sense, so the voltage sense and current sense part, the INA 226, is measuring basically the output capacitor draining. I think I should, an enhancement to this in future, I could probably put a relay across the output rather than using the output enable pin of the NXA66. That way the voltage would always be displayed because there'd always be something coming out of it. At the moment there's nothing coming out of the NXA66, so all the current sense chip can see is the discharging of that output capacitor, which is interesting in itself but probably not what you want to see. Let's put output enable back on. That was the wrong switch. There we go. 3.3. Let's compare that to what the iTech DC load is saying. It's saying 3.3296 and we are seeing 3.331, which shows that there's very low losses in the cable. I'm assuming the difference is the losses in the cable really. It's largely down to that. Okay, so let's have a quick look at the firmware options. If I press the button here on the rotary encoder, it cycles through the menus. First option is calibration, which is currently set to 0. What I can do there is adjust the calibration value for the INA 226. Now, to see that working in action, it's best if I actually switch some load on. So going up to the iTech unit here, I'll dial in, it's on constant current, which is what I want. Let's dial in a lowish load. Let's put in 0.5 amp and switch it on. And there we go. It's now providing 0.5 amps worth of load, and it's actually measured that it's doing 0.498. And if I go down here and I look at my output display now, which is now showing current, and it thinks it's 0.48 instead of 0.498, you know, a difference of about, well, what, 20 milliamps. And I'm assuming that the iTech's actually accurate. Let's put in a calibration value and see if we can make them match. Basically, I just go around my menu, options, I just twist to the cal again, enter, and the current display now switches to the top LED, and I can alter the calibration value to match. So let's jack it up. Obviously this is a current, it's going to be a non-linear value here. This is kind of a brute force approach, a single calibration approach regardless of the current drain, even though the actual value is likely to be non-linear. So if I set it to a value that corresponds to the sort of loads I use, there we go, down a bit, 498, and that's now saved in the EEPROM of the AppMega there, so it'll be the same every time. So now we match up with the measurement shown by the iTech, and what I've done there really is calibrate for the inaccuracy of the current sense resistor. I can't, it's a very low value and difficult to measure 2 milliohms, so setting a calibration value like this against an instrument like the iTech is probably the best way to do it. Right, a quick run through of the other options in the firmware menu. We have IL, that's current limit. If I select that, then it's telling me that I want to set the number of amps in the limit first. The default's 20 amps, which is the full range. So I can set the full range down to, let's say, 10 amps, for example, and then press the button, and it's now telling me I'm setting milliamps. So I can set the milliamp range for it. I'll leave it at 10 amps. I'm not going to go higher than that today in the testing because I can't supply that much power from my bench power supply. Other options in here, we have data logging. This says the frequency of the data logging, currently every 1,000 milliseconds. You can set that to whatever you want in steps of 100 milliseconds. Go down to 0 and data logging is switched off. Let's go through to the LED. That's just the brightness of this display. You can set that. That's a feature of the display driver. 15 is the maximum. I'll leave it on that because of the problems we're having with lighting today. Go through again. Fan, I can set fan degrees C upper limit. That says the fan will come on if 40 degrees is sensed or higher. And the lower limit, it will go off when the temperature drops back below 30 degrees. Let's have a look at the next one, and I can have a quick look at the current temperature, which is showing 24 degrees. That's the measurement from the NCP, what did I call it, 9007, I think that's the right one. Check my website for the actual part number if I just got that wrong. 24 degrees is virtually nothing. It's only showing, you know, that's at half an amp load. So now let's jack the load up and see what happens to the temperature and the actual regulation of the output voltage. Right, so I'm currently showing a load of half an amp, and I'm going to turn that up as far as I can go without triggering the current limit on my bench power supply. Let's show you the load at the iTech and the input power supply. So to turn up the load, all I do is wind the knob here, and it's currently got the underline underneath the hundreds of milliamps display. So that means it'll step up in steps of 100 milliamps. And you can see the load being the current coming out of my bench power supply there is rising at the same time, and I can't go any higher than 3 amps there. I'll stop when I get close. So we've got 3 amps coming out of the NXA66 at the moment. Now 4, 5, 6, and you can see there's losses in the cable here. As we're at 6 amps at the moment, you can see that the voltage being sensed by the iTech is 3.1. It's dropped down. But if you look down at the voltage measured at the output of the NXA66, it's still around 3.3. So the cabling has actually got some losses in it. Well, obviously it has, it's not a perfect cable. Let's go up, and at my power supply, I'm going to be hitting the limit soon. 7 amps, 8 amps, 2.7 coming out of the bench, and I'll stop around 2.9. I'm going to stop soon, 8.8, 8.9. I'm going to stop there because it's getting very close to my limit. 2.96, 2.97 coming out of the power supply. It's stabilised around I'll call it 2.97. It must be very high 2.96s. And it's just switched on its cooling fan. Very brute force thing. It's either on and loud, or it's completely off. The iTech's much better. It has a PWM fan inside it, and it just winds up as necessary. So let's go down and see what's going on down here, and we have 3.288, so the regulation of the voltage is still very good at a measured 8.95 amps output. So what we can do here actually is measure the efficiency. Let me grab my calculator, and I'll put the light back on as well. Okay, so the iTech, I don't have to calculate the power for that, it's telling me. You can see down here, it's telling me that it's seeing 27.42 watts at the output. I'm not going to use that because that's going to be the power dissipation that it sees, which is after the leads, obviously, and there's loss there. So I want to calculate the efficiency of the unit, so I don't want to take into account those output losses. So what have we got here? I can just about see that. Let's put it through the filter. 3.288 volts at, oops, so we have 3.288 times 8.954, 954, let's bang that into my calculator. I grabbed a bit of a historical calculator here. 288 times 8.954 equals 29.44 watts. Equals 29.44 watts. Right, so that's our that's the power that's being supplied by the power supply, the NXA66. Now we need to know the input power. We have 12 volts, 2.98. So let's put that into the calculations. We have 12 times 2.98. Sorry about all the slow bits here, because I'm having to lean over and generally mess around to get these things done. We have 35.76 going in. So the difference between those is the losses basically inside the board. So the efficiency as a percentage is simple to calculate. We just work out what percentage that is of that, and we can do that by 29.44 divided by 35.76 times 100, and we have an efficiency at 8.95 amps of 82%, 82.3, which is really very good. 82.3%. Not bad for you know, a high load, and the regulation at 3.288 is very close to 3.3. So overall, I'm very happy with the stability of this thing under load. That's good. So I think as a last quick demo, I'll show you the fan coming on. Why not? Actually, before I can demonstrate the fan, I've just realised I'm going to need to turn down the load, because at 8.9 amps and 2.97, that is very close to my bench power supply limit. And when the fan activating is going to draw current, which is going to trigger that over the 3 amp limit and cause the thing to cut out and go all horribly wrong. So I'll just turn down the iTech load right back down to just an amp. Let's go down to 1 amp. 1.1, 1.0. No, that's better. So I won't trigger the thing. I did that before when I was testing before I made this video. I just realised, and I thought I'd broken the thing because it just started going all wild. And I looked at the bench power supply and realised I'd cut the thing out. Right. Okay. So no problems here. So back to the fan. Let's say, oops, fan. Let's make it come on at some silly low level, like 20 degrees, off at 40, so that's never going to happen, is it? Let's bring it back down to also somewhere around like 10 or something. And the fan immediately comes on. I'll show you actually, turn the light on, and the fan's immediately switched on. So it just shows that works. Okay, so I think I'm done here actually. I've showed you just about all the features of the board, showed you it's under load, and I'm very pleased with the way that the NXA66 has performed. So I think the next step for me will be to get a case for this. It obviously needs to go into a case, and I need to you know, mount the switchgear onto the front of it. And I'll make a case in Inkscape and get it cut from acrylic. So until then, I think I'm all done. If you want to build one of these, the schematics, the Gerbers, and the full bill of materials and all the information that you need to do this is on my website, which is andybrown.me.uk. You can see the address at the end of this video, and please visit, read the write-up, and I hope you've enjoyed the video. Thank you very much for watching.